So I'm going to talk about a quantum approximate optimization algorithm. This work I've done with my collaborators, Jeffrey Goldstone and Sam Gutman. And so what I'm interested in, I don't know why it's scanned like that. It's always a little off on the bottom, I'm sorry. What I'm interested in is combinatorial optimization. This is a high-level talk. I'm not going to go into super detail. I hope you can follow me. So here are problems where we have n bits and m clauses. And we have the bits we represent by a string z. These are 0, 1, or 1 and minus 1. It doesn't really matter. And there's a cost function, which is the sum of individual cost functions from m clauses. And each of these acts on a subset of the bits. And it is defined so that it is 1 if it satisfies and 0 if it does not. And I am interested here in maximization, not minimization, which is kind of interesting because often people have gotten used to wanting to find ground states because there's something natural about finding a ground state in a quantum computer, but that's really not a good language for me to use here, as we'll see. And the reason for that is because I'm interested in an approximation ratio. And what the approximation ratio is first we define the maximum of the cost function, where that's very hard to find, but it exists. The maximum of the cost function. It's the maximum of all 2 to the n strings of the cost function. And the approximation ratio is the value of the cost function that your algorithm outputs divided by the maximum. And since I'm interested in this ratio, you see, if we talked about minimum, this really wouldn't work too well if the minimum was 0. So we like talking, when we talk about optimization, approximation ratios, we really want to talk about maximum. Now, what we want to do is we want to make that big. Now, in the last number of years, 10 years or 15 years, have been really interesting results in classical computer science about the difficulties in finding good approximation ratios. And we know, for example, that if you could go improve upon certain algorithms for finding good approximation ratios, that either p would equal np, or in other cases, the unique games conjecture would be false. So there are really interesting theoretical reasons to care about these approximation ratios. But there are other reasons. There's another reason, and that's that I'm interested actually in the world building a quantum computer. And if you build a quantum computer for optimization, finding the absolute best solution may not be what you really want the quantum computer for. You may be very happy with a good approximation ratio. And maybe sometimes they say the best is the enemy of the good. And maybe we've been too obsessed with looking for algorithms that produce the best solution, when we really should just be looking for good solutions. So now I'm going to talk about a quantum algorithm for this, and I would like to give you the ingredients of the quantum algorithm. Well, first of all, we have this cost function. And given the cost function, there's a unitary that depends on an angle gamma, e to the minus I gamma c. Now, the reason gamma only is an angle is because c has integer eigenvalues. So if gamma wraps around beyond 2 pi, this unitary will just repeat on itself. And note that this unitary can be written as a product of m unitaries because each of those c alphas commute. So this thing is actually a product of unitaries, each of which involves the bits in the clause alpha. So this is a product of m unitaries. Now, there is another operator I would like to consider, which is the sum of the sigma x's. Okay? I call that xj stands for sigma x, and I call b the sum of the sigma x's. And now there's a unitary, which is u of b beta. Beta is also an angle because this has eigenvalues Each of these has eigenvalues 1 and -1. And if you have n of them, you still have integer eigenvalues. So this is now, it can be written e to the minus I beta b as the product over n individual rotations of individual qubits by angle beta. And each of these commutes, also like they do here, and so this is a simple operator to imagine constructing. And the reason I'm writing it out and I'm belaboring this is because I believe these are very easy to make. And I am interested in building a quantum computer. And the fact that these are easy to build, I think, is important for my discussion. The other thing I would like to consider as an ingredient is the state S, which is the uniform superposition over all strings Z. And that's also an easy to construct state. So now I would like to start to discuss how the algorithm could work. So first of all, I would like to have an integer p, which is 1 up to anything. And for each p, I want to define p angles gamma and p angles beta. And I write this collection of angles as a vector. It's just notation. I'm not thinking of this as a vector in a vector space. It's just notation for this collection. And this is, if my script was, I could boldface this if I knew how to do tech or something, but I don't. So I have to put arrows. So that's just what this stands for. So now consider the state gamma beta, which is acting on the state S. First you act with the unitary with C, with angle gamma 1, and then you act with the unitary with B, with beta 1, and then you do it with gamma 2, beta 2, ... So it's a product of these things. Now, note that to construct this state, the required circuit depth is not much because the circuit depth of U of B beta is 1. Because it's a bunch of commuting operators. And the circuit depth of UC gamma is at most P. No, it's at most M, excuse me, it's at most M. And so, but it isn't, it's much less than that if you organize the terms appropriately. But at worst, it's this. So the required circuit depth here is MP plus P. Now, I would like to consider the quantum expectation of the cost function in the state gamma beta. So let's just consider this. All right? If there are any questions, please ask. Okay, we're good? Now, I would like to consider an object which I call M sub p, which is the maximum over gamma and beta of Fp gamma beta. You know, C is the cost function, so kind of you can see we want to make a quantum state that makes this big. So imagine, so let me define MP as the maximum over gamma beta of Fp gamma beta. Well, the first thing you'll notice is that MP is bigger than MP minus 1. Why is that? Because this is a maximum over 2p variables. But if I go to p minus 1, it's the same function with the last 2 variables set to 0. So the optimization at p minus 1 is a constrained version of the optimization at p. So the optimum can only go up or stay the same. Does this make sense? Okay? Now there's another thing here which you can show, and I'll explain why, is that in the limit as p goes to infinity, MP is C max. As p goes to infinity, you can achieve the maximum of the cost function. The way we know that, let me just outline the argument for that, is that because if you think about the adiabatic algorithm, but now don't think of it as going for the minimum, but for the maximum. And you can think of the operator B as the, as the beginning Hamiltonian. Then the state S is the eigenstate of the beginning Hamiltonian with the largest eigenvalue. And by the adiabatic theorem, there will be an adiabatic path where I write an adiabatic path which uses B and C, linear combinations of those, and will take me if I run for a very, very long time, to the maximum to the state with the maximum eigenvalue of C. And this you can think of as a trotterization of that path. So it means that in the limit as p goes to infinity, you do go to C max. But that's just a fact, which I'm not that interested in, because I'm interested actually in this algorithm for p small. Like I'm going to be caring about p1, 2, 3, low depth. Okay? But that's just an interesting fact that as p goes to infinity, it produces the perfect answer. So given these facts, we can imagine an algorithm. So let's think about this quantum algorithm with angle search. Okay? The first thing we do is fix p. Make p whatever you want, 3, 2, 100. And start with some angles, gamma, beta. Now, use the quantum computer to make this state. I claim that's not too hard to do, because I've shown you the ingredients, and they're all fairly simple. And then measure to get a string z. You make the state, you measure to get a string z, and then you just compute c of z. Now, if you do that a few times, you do it again with the same angles, you're going to get that function, a good estimate of fp of gamma and beta, which was, remember, the expected value of c in this state. In fact, I could tell you that you don't really have to make many calls, because there's a concentration bound which I will discuss later, which says that almost every measurement of z, when you produce this state, every z value will have the same value of c of z. I'll explain that later. Okay? But anyway, so now you get an estimate of the cost function. Now you go and you change your angles and you try again. So you have this meta program running outside the quantum program. And for example, maybe you gradient ascend, or maybe you make a grid, or you have some kind of MATLAB routine, and you just try to maximize your angles. And so you keep repeating with different angles until you get near the actual maximum. So that's one idea for a quantum algorithm. Now, you could worry that this function has very narrow peaks, exponentially narrow, but it doesn't, because we can also estimate how jagged this function is. And it's only polynomially jagged. It's not exponentially jagged. So that means that even if you decided to do an angle search by making a grid for low p, you can do that efficiently. Okay, so that's the algorithm in some senses. Make this state, pick your angles to make this as big as possible, and see how you do. Yeah?
You're interested in the string, or you're interested in the value of the max? If you're interested in the string, you need to measure that to get them?
That's right. That's right. I'm interested in the string, so you have to measure the state to get the string, which you can then classically turn into the value of the cost function. I'm interested in the string. Okay? So, that's one version of the algorithm where you just search over the angles. But there's another way you can do it, which is actually, if p is fixed, we can classically pre-process and determine the best angles in advance. So let me show you how we do that, how you could classically pre-process and determine the best angles in advance. And I'm going to do this with an example. Okay? So the example I would like to discuss is max cut on 3 regular graphs. So remember, a 3 regular graph means every vertex has 3 edges coming out. It's just, I want to do an example because I think if you explain something by example, then you can just generalize to everything. Okay? Now, in this case, the cost function, max cut, if you remember, is really the problem where you have a graph, and on each vertex, you have a spin, which is plus or minus 1. And what you want to do is you want to maximize the number of edges that disagree. So max cut is like an anti-ferromagnet, if you're thinking of the ground state, but I don't want to think of the ground state. So what I want to do, though, is here I want to maximize the number of disagreements. So if you look at it as z as a plus or minus 1 variable, then this is the cost function, because if the two z's are both plus 1, this cost function is 0. But if one z is a 1 and the other is a minus 1, the cost function is a 1. So I could call this max disagree, or we can call it max cut. That's the same thing. Okay? So what I want to do is I want to make this as big as possible. And max cut's a very well-studied problem. In classical computer science, we know a lot about it, even on 3 regular graphs. So let's see. I'm going to show you now how we determine the angles in advance. So let's look at p equals 1. Again, now we're going to another example. So p equals 1. Let's look at the contribution to edge jk from the algorithm. So p equals 1. So I'm not going to put a 1 on these things. Gamma and beta are just the angles, gamma 1 and beta 1. So here's the state. And I want the expectation of this in the state S. Note the state S is a product state of eigenstates of sigma x's. Okay? That's all it is. So let's look, for example, at that central object, e to the I beta b, zj, zk, e to the minus I beta b. That's equal to, you see, the parts, b is the sum of all the sigma x's, but the b's which involve bits other than jk, they commute through. So this thing is just e to the I beta xj plus xk, zj, zk, e to the minus I beta xj plus xk. Okay, because the others commute through. So this then just rotates these two, and you get cosine 2 beta zj sine beta yj cosine 2 beta zk plus sine beta yk. So note that that first conjugation of the central operator did not change the locality. It's still just bits j and k. Now let's conjugate with e to the I gamma c. Okay. Now, e to the I gamma c, c now is a sum of terms, some of which involve bits j and k, and some of which do not. Well, the ones that do not involve bits j and k at all commute through. So the only thing that doesn't commute through are the terms in c which involve bits j and k, the term itself, or anything connected to j and k. Okay. But I'm on a 3 regular graph. So there are only 3 possibilities that j and k, what comes out of them, let's look at this one first. Like j is connected to this bit, and k is connected to this bit and this bit, and they're not, there's no, and they're different. So this is, this is j and k, and this is bit 19, 30, 50, and 100. But it could be that, did I not draw something? Yeah, I forgot the triangle on this. Oh, that's so terrible. Sorry. I spaced out. Sorry, there's supposed to be a little triangle there. Gee, sorry. Yeah, there's a little triangle here, okay? Yeah, there's a triangle here. Or it could be that, bit j is connected to 7 and so is k, and bit j is connected to 10 and so is k. Sorry about that. I lost my triangle on the top, okay? So there are really only 3 possible subgraphs. Okay, so I look at an edge, and it's either of this type, which has the triangle, or this type. Okay? Only 3 possible subgraphs. So each subgraph type is a function of gamma and beta, and it doesn't depend on n or m, each subgraph type. It only depends on gamma and beta, and the first one, and it can be evaluated on a classical computer looking at a 4, 5, or 6 qubit system. Because if you go back, this one involves 4 qubits, 1, 2, 3, 4. This one involves 5, 1, 2, 3, 4, 5. And this one involves 6, 1, 2, 3, 4, 5, 6. So by just looking at a 4, a 5, or a 6 qubit system, I get 3 different functions of gamma and beta. And they can be evaluated. Then I can evaluate F1 of gamma and beta because I take the graph, okay, and I count the number of subunits which are of this type, or this type, and I add them up for any given graph. And then I can, on a classical computer, evaluate this function and determine the best angles, okay? And once I know the best angles, I can then run the quantum computer to produce the state and measure the string. So the way it works is you can classically pre-process, determine the best angles, and then you can actually run the quantum computer to produce the state. And at p equals 1, the QAOA will produce a cut that is at least 0.6924 times the optimal cut. Now, in order to see that, I also would have to show you how we put a bound on the denominator. We can upper bound the denominator because by counting the number of those subgraphs, because if it has a little triangle in it, the subgraph, then you can't have a perfect cut. It has to be frustrated. So what we can do here is actually, for any given graph with a certain number of those different types of subgraphs, I can put an upper bound on the denominator. And therefore, we can actually compute the approximation ratio. And we can prove that we get 0.6924 times the optimal cut. And I think what is really worth noting here is I just did this for all instances of 3 regular max cut, independent of n. I did it for an infinite number of instances. And I think this is really the first time that we've ever seen a quantum algorithm analyzed for all instances of a combinatorial optimization problem of any interest. Okay? Now, this, and another thing I want to say about the 0.6924 is it improves on random guessing, which gives a 0.5. Now, it's not as good as the best classical algorithm for this problem, but, you know, for max cut, up until Gomans-Williamson, random guessing was the best that could be done. So, you know, the achievement of the Gomans-Williamson algorithm was that it improved on random guessing for max cut. And it was a provable improvement. So this is not as good as Gomans-Williamson. Gomans-Williamson, for those of you who know, is a classical algorithm for max cut, which is guaranteed to produce an approximation ratio of 0.878 or something. But it's actually even better if you restrict to 3 regular graphs. It's like 0.9 something. So it doesn't achieve this. But first of all, this is only p equals 1. And if I go to p equals 2, I have a stronger result of like 0.75 or something. And at p equals 2, I have to look at more complicated graphs. It only gets better. But it gets much harder to analyze because if I look at p equals 2, I have to look at a subgraph which has 14 qubits. And then once it gets beyond 14 or however many qubits, it gets much harder. However, the analysis of the subgraphs is n-independent if you have graphs with fixed degree. If your subgraphs, if the degree does not grow with n, then for every p, the analysis you can classically pre-process efficiently in n, because the requirement may grow badly with p, but it is independent of n. So this algorithm is efficient for any p on fixed degree graphs to classically preprocess. Okay? Now, let's look at, just to show you another example, which I think is interesting. Let's look at let's look at max cut on a ring. I call it a ring of disagrees because the edges want to disagree. It's max cut, it's n bits. Now, I know how to solve this. 1 minus 1, 1 minus 1, 1 minus 1. I just alternate the spins. Okay, so there's a perfect solution here. But what we could show is that the QAOA gives an approximation ratio of 2p plus 1 over 2p plus 2, independent of n. So that's also interesting because it's saying that here is a problem we can actually analyze. And the approximation ratio is independent of n. And I would now like to say something about the concentration bound. See, at p equals 1, we get an expected value of the cost function, which is 3/4 n. Because if p is 1, you get 3/4. At p equals 1, we get 3/4 and, what is this? What type of English is this? Note at p equals 1, we get 3/4 and, I guess. And for large n, almost every string satisfies 3/4. But I should really proofread my slides. Okay, sorry. We get almost every string satisfies 3/4 of the bonds. So why is that interesting? Because you see, the expected value of the cost function, I'm telling you, is 3/4 n. Well, one way you could achieve that is to have 3/4 probability of having the perfect string and sort of everything else total crap. But that's not what happens here. What we can show is that at p equals 1, every string you output satisfies 3/4 of the bonds. So what this algorithm is doing, it's not a failed best algorithm, which is with low probability producing the best solution. What it's doing, it's producing strings with exactly that approximation ratio. And I could show you, we could prove that this thing has a concentration bound. That's why when I said before that what you needed to do was run the algorithm, find the string, and then do it again. You don't really have to do it again because every string has the same value of the cost function. When I say has the same value, I mean I could make that precise. But, okay? So that's why I think this is truly an approximation algorithm and not simply but it's interesting because, in classical algorithms, sometimes if you would like to get a good approximation, what sometimes you can do is run an exact solver and just terminate it early. Run an exact solver, which would take forever to find the solution, and then just stop after a day and see what it gets. Depends on the nature of the algorithm, whether it's making improvements. But that's not what we're doing. That's just not what we're doing. Okay, so is there any question about max cut? Okay. So now I want to talk about another problem, which I call max E3 lin 2. So let's make sure we can all understand what this problem is. E3 lin 2 means I have equations, and there are n variables and m equations, and each with 3 variables. So this E3 means every equation has exactly 3 variables. Lin 2 means it's linear algebra over binary variables. So now I'm calling the zi 0 and 1. We can adjust to that. Okay? So every equation is of the form zi plus zj plus zk mod 2 is a 1 or a 0. So the way you specify an instance of E3 lin 2 is you specify a collection of triples and a 0 or 1 for each triple. The 0 or 1 tells you whether that triple of bits should add up to a 1 or a 0. Now, this problem, is there a solution, is in P, because this is linear algebra. And I can solve these equations by Gaussian elimination and determine if there's a solution. So this problem, as a decision problem, is there a solution? There's a polynomial time algorithm, which is just do linear algebra. You can add, mod 2, it's fine, until you solve it. And if there's a solution, there is one. So I'm interested in a different situation. I'm interested in a situation where the number of equations is more than the number of variables and there is no solution. And the task at hand is to find a string that maximizes the number of satisfied equations. Okay? Now, it is NP hard to find the optimal solution, so what we're going to do is try to find a good solution. Is the problem clear? The E3 ln 2? So, now I'm just going to tell you a story. I'm not going to show you the details. So let's look at approximate optimization here. First of all, let me give you an algorithm. Guess a random string. Well, if you guess a random string, then every equation has a 50% chance of being satisfied. Because if you guess a random string, of the 8 possible settings of those random strings, 4 will satisfy the equation and 4 won't. So that automatically gives a 50% approximation ratio. So guess a random string achieves a half. But in 2001, it was shown that if you could achieve an algorithm that got a half plus epsilon in an efficient algorithm that would get an approximation ratio of a half plus epsilon, that would imply that P equals NP. That's remarkable, right? Because that's saying that, this is a beautiful classical result. It's saying that you cannot improve on random guessing. I mean, you could improve maybe a little bit, but you cannot improve. If epsilon is any epsilon could be 10 to the minus 20. So that means that, if your algorithm achieves 0.5000000001 and it's independent and it's efficient, then it would imply that P equals NP. And that was shown in 2001. So that means that this is a very hard barrier to break through. Okay? Because we're right at the P versus NP barrier, a place I don't want to be. But I found myself there. So anyway, we decided to look at a variant of this, which is called bounded occurrence. Bounded occurrence means every variable is in no more than D equations. Now I've given you something. It's not the most general problem. I've told you something. Now that I've told you something, you might be able to make a little improvement. And what you can then do, in 2000, there was an algorithm due to Hostad, which got a half plus constant over D for the approximation ratio. See, that's not as good as this. It's not a half plus epsilon because it depends on D. But this was achieved in 2000. Okay? Are we with me? Good. So then we showed in the fall that the QAOA, we showed how to pick angles by pre-process. We worked it out. We analyzed the algorithm, and we could achieve a half plus constant over D to the 3/4. This is in 2014, last fall. And at the time, we were kind of pleased with ourselves because we, at the moment, had a quantum algorithm for all instances of a combinatorial search problem, which was provably better than the best-known classical algorithm. Now, but there was another thing we did here, which was the following. We actually showed that the computer was going to output a string that satisfied this many times m of the equations, where there are m equations. So what we actually did, we computed an approximation ratio, but we did it in a sneaky way, because we actually showed that since the algorithm would produce a string that satisfied this many times m equations, it means that a string had to exist which satisfied that many of the equations. So our result was what we call existential. We said the algorithm will produce it, but not only that, but a string that satisfies this many equations exists. And then, well, Scott blogged about it, and the computer scientists noted that we had an existential result. And since it was, then they said, okay, let's see whether we can find an existential result for this problem using classical techniques and then turn that into an algorithm. And 10 of them got together and did it. Okay, so that happened in 2015. So then, well, I wanted to put my collaborators' names up again, because, you know, they're my buddies, Jeffrey and Sam. So we then said, okay, better go back to work. And we then improved the analysis of our algorithm. We didn't change the algorithm, we just improved the analysis. And we achieved the half plus 101 d to the 1/2 log d. So our algorithm still, it's not as good because of the log d. Now, I don't know whether that log d, we can get rid of it or not. I mean, I know we couldn't get rid of it trying very hard. And I got sick of it. But whether someone else could improve it is, you know, I don't know that. Or whether we could in the next life improve it is also possible. But for the time being, we're sick of it. So, but we have another little result here, which I think is somewhat interesting. And that's, we looked at typical cases, random. But let me tell you what I mean by typical here, because it's not the usual definition of typical. What I mean by typical is I take E3 ln 2 and I fix the factor graph. And now, so for any given graph, I now average over whether, or no, excuse me, I randomly select, because that's what I mean by typical, whether the equations add to 0 or 1. So for a fixed graph, there are 2 to the m instances, because each of the m equations could either sum to 0 or 1. So we pick uniformly from the 2 to the m equations for every factor graph. And that's what I mean by typical. And that's the reason I'm stressing that is because if you look at the classical analysis that appeared early on, some of the issues they have to do with small triangles and stuff like that. And so this says even if you have all small triangles, this is the typical case. And I believe that our constant here is bigger than the constant that the classical guys have. But they don't give their constant. They just say they have a constant. But we kind of estimated it. It looks like it's much smaller than this. But now you can say, can we get rid of the log d? You know, we'd like to do that. But if there exists a 1/2 plus constant over d to the 1/2 for sufficiently large constant, then p equals np. So, you know, and now I assume that the classical algorithm, although they don't give that constant, is not bigger than this constant. Otherwise, they would have had a different abstract. And so anyway, you know, we're kind of right at the edge there of making things hard. But so that's where we are. But this is all p equals 1. And because it's harder to analyze p equal higher p. But I think it's interesting that, that we can, you know, actually get results for very low p. Okay, so the future. Well, we want to analyze higher p. Well, that's really hard, but we'll try. I want to look at other problems. You know, I've talked about E3 ln 2, max cut. There are other problems that I'm interested in. I'm interested in problems that are not only at the p versus np boundary. Now, the other thing I want to do is I want to run the QAOA on a small quantum computer to study its performance. Look, the world is about to build perhaps small quantum computers. We've been hearing about industry getting interested in this. And if you have a small quantum computer, it's a gate model quantum computer, what are you going to do with it? Well, I'm suggesting that you run this algorithm because it has very simple gates and a very low circuit depth. So it may require almost no error correction if you run it at p equals 2. You know, you just have these simple gates. And now the other thing I want to do is study fault tolerance of this thing. And so let me tell you something about that. I've been working on this with a student of mine, Adam Bukatz, and with Peter Shore. And you know, if you go back to the analysis that I had of how the algorithm is set up, did you see the way there was like a central operator and then it got conjugated by other things, but it was maintaining a kind of locality? Well, that actually is enough to show that if you have, for example, 1 qubit errors, suppose you just start introducing 1 qubit errors all over the place, that what they will do is they will reduce the expected value of the cost function. Let's suppose it will reduce it by an amount that depends on p, but not an amount that depends on n, except for the overall scaling. So what happens here we can show is that even though errors can make the fidelity of the final state go down with n, the expected value of the cost function doesn't. Well, it has an n in it, so I mean, it scales with n. You know, if you think of it as n times something, the times something thing doesn't go down with n. So that's very interesting because it means that this thing has an inherent fault tolerance, which doesn't grow with n, only with p. And again, I think that makes it a really interesting thing to try to implement on a small-scale quantum computer. So what I would like to see is if someone builds a small quantum computer, they say, okay, let's run E3 Lin 2 at p equals 10 and see what type of constant you get and how does that compare with what type of, or does the log go away or whatever. So anyway, I think that there's a future here. And I'd be interested in anyone else, telling me what they think about doing here. Okay, that's my talk.
Questions? So I guess gammas, they can be thought of as sort of times for which you apply this sort of Hamiltonian that defines your cost function. Yeah. So if I give you sort of a limit on the sum of all the gammas you could sort of apply for your entire sort of algorithm, that would be sort of the total time over which you would need to sort of apply this cost function. And then suppose you do just some naive adiabatic algorithm over that time. How does this compare to this? Do you think it will be strictly better, strictly worse, or incomparable?
Well, I think that this will look, if you take the adiabatic algorithm and you can then say, let me approximate it by trotterization. If I trotterize it, it looks like this, because it's an alternation of those terms. That's what you get in the trotter approximation. Now, I think this can only be better because if I insist that I'm choosing the optimal angles, it can't be worse. I mean, it can, if you trotterize the adiabatic algorithm, I can only do better because I'm optimizing. Now, I agree that this looks like a trotterization of the adiabatic algorithm. However, at p equals 1, we have results. And at p equals 1, I don't think it's a trotterization of the adiabatic algorithm because it's just one and the other, and that's it.
More questions?
So this analysis you mentioned about enumerating these little subgraphs and analyzing them one by one, do you think that's something that could be automated and done by a classical algorithm?
Sure, but the only thing is that the requirements grow. If you're not on a at a 3 regular graph at p equals 2, you have to go to 14 qubits. Now, we have in our paper a formula for what happens as you go to higher numbers. So I think unless you can do better than simply analyze it as a quantum subsystem, if those subsystems have more than 20 qubits, that's going to be hard. But that's another thing you could do though with a small quantum computer. You could analyze the subgraphs and then send them to a big quantum computer. You can analyze the subgraphs with a small quantum computer and then determine your angles in advance and then go to the big one. But I mean, when I say it's efficient, it's efficient in n, but it's not efficient in p. But from the computer science definition, it's efficient.
More questions? What do you look for good angles? I didn't understand this point. When you look at these sub-problems, what makes a good set of angles? It seems that they could be good for the weight 4 system versus the weight 5 system versus the weight 6 system. Why the same angles?
Oh, well, no, I mean, you have 3 different functions, right? So, when I gave the 0.69, that was worst case. I said, now we're saying let's consider the worst, you have a certain number of each subgraph type. That's worst case. So, if you were going to run the algorithm and you had a single instance, you wouldn't use those angles. That was worst case. So I think if I gave you any individual instance, you would find the optimal angles for that instance. But that's a worst case result. Yeah.
So I love the idea of a low circuit depth algorithm that could be run productively on near-term small quantum devices. But I'm curious, suppose we had 10, 20, 100 qubits, and you studied the performance.
Yeah.
How far would you have to get before you could, even in principle, get evidence that it was outperforming classical algorithms?
Well, suppose that, let's suppose we looked at E3 Lin 2, and we saw, let's suppose we went to max cut, and at 100 bits, we saw that we always beat Gomans-Williamson. I don't know. Or suppose we went to, and now you could say, well, you're only at 100 bits, so I don't really know. Maybe it'll turn around. That's what they would say when you go to 10,000. But, it'd be interesting. Or what if we suppose that, we do E3 Lin 2, we go to p equals 10, we don't see evidence of the log, and we look at the constant, and it's better than the classical algorithm's constant. Then you'd say we have a better algorithm. But I mean, that would be numerical evidence. But I think you could get an indication. But I'm still not going to claim that a 100-qubit quantum computer is going to outperform a classical computer for these problems, because there's always, at 100 bits, you're probably going to be able to find a classical algorithm that does very well on any kind of combinatorial search. I mean, there are certain problems that are really terrible, like number partitioning or something, but these kind of max cut problems, classical computers can handle them very well at 100 bits. So we would have to look for indications that we were scaling better, and then say, well, wait, when we get to the realm where the classical computers cannot function as well, maybe we'll beat them. Does that make sense?
One more question?
Sure.
Hi. Yeah, I was just wondering, do you know if the performance of this algorithm correlates with Gomans-Williamson?
Correlates?
Like on specific instances. So you did a worst case analysis, but you could in principle analyze it using a classical computer on specific graphs, right?
I don't know. I don't know. Because Gomans-Williamson can always do better than its lower bound.
Sure.
So you could say, what's the correlation between the performance? If I gave you a sample of random graphs up to 20 qubits, I think Cedric and Hanschwan looked at some 3 regular graphs at 18 and 20 bits, right? But I don't have an answer to your question. I never did that study. I don't think anyone else did, but you could do it. You could see whether instances that are hard for Gomans-Williamson are hard for this. I don't know.
And one more question?
So I was wondering if you could speculate, I guess, on that first point, analyzing higher P. And as you mentioned that, as you go to large P, you're definitely going to get to 1, or the ratio
Right.
should be get 1. You could use the adiabatic algorithm to sort of estimate that increase, right?
Well, yeah. I mean, the problem is that I can, if I give you any given instance, I can prove that as p goes to infinity, it's perfect. But that p may be exponential in n. So, yeah, so, it's just a proof technique. It could be that p is exponential in n. And this algorithm may outperform that. So, I don't know. I'm hoping that at low p we can. I was very surprised that at p equals 1 we had results that would be on random guessing. So my hope now is that still at low p we can still continue to make progress. If p has to grow with n, well, it may have to. But even if p is growing like n, it's okay. But if p has to grow exponentially in n, then obviously you have big problems. I mean, it's possible that p has to grow then because, if you have a very big graph, and you could see that we have this thing, the locality of the subgraphs that we look at grows with p. So it may be that it has to come around and start seeing loops and stuff. So p has to grow with n in order to get really some good results. I'm aware of that. I have trouble analyzing that. But yeah, so the hope there would be if p grows with n, okay, that's still polynomial resources. If p has to grow exponentially with n, that would be bad news.
All right, I think we're out of time, so let's thank Eddie again, and have a good afternoon.